this talk is titled In Situ Resource Utilization: Learning to Make Architectural Bricolage in a Wasteful World. Let's see if I can move to the next slide. Okay, so I want to kick off with a slide of the Crystal Palace, which is this turning point in UK's history, right? It's imperial project, but which is kind of terrifying, but it's also this moment of huge scale industrial production. So at this point, we can make as much stuff as you want to, kind of, right? Like, what's the ceiling? What's the limit for the quantity and kind of exuberance of the material world that we're kind of transforming, mining things across the planet and then turning them into these kind of crazy, huge industrial projects. The Crystal Palace is made of all of these fragments, as I'm sure you all know. It's designed like a railway system almost, right? Like every piece is very easy to produce, and it's mass production coming together in one of these first examples of like a greenhouse, but with glass and steel coming together on a huge scale. And inside the Crystal Palace, it was exhibiting like in this industrial might as well. The building is a symbol of industrial might, and the exhibitions within it are opportunities to kind of marvel at this new kind of planet of huge scale production that was being born. So my thesis at MIT kind of looks at the backside of that industrial production, thinking about waste. So I've been looking at like how buildings and the built environment comes apart. So if you think of New York, each year there's about 31 million tons of waste being produced. In 2015, of that, a lot of it is industrial, municipal waste. But the construction industry contributes more waste than any of those other areas. A lot of that comes from roads and bridges, which have got a lot of concrete. So when you rebuild a road or bridge, there's a lot of concrete that comes out of that. But buildings also contribute a lot of concrete and timber waste. What happens to that is it's typically taken to landfill. If you piled up all of the concrete waste from New York that it's produced since 1989, and there's a thing called the angle of repose. So when you make a pile of debris, it kind of wants to strike this angle. If you piled up all of the waste, you'd get a building that's taller than the Empire State Building. That's just the concrete that's come out of New York since 1989. If you look at glass, since 1955, and you put all of the glass that was taken out of New York or demolished from New York, you could cover like a 6 km square of Brooklyn. It's like the city had that glass at some point, but it's just been demolished because so many buildings have been taken out. Really recommend this book, Geographies of Trash by Rania Gosen. That was one of the formative kind of ideas and people at MIT who got me thinking about this kind of like waste that's coming out of a very industrialized society that we live in. But on the flip side of that, they also get like artists, right? So Pablo Picasso taking these like mass-produced pieces and then turning them into art or playing around. And this is bricolage. So this is that bricolage part of the title. There's some amazing examples of the Wright brothers where they were bicycle mechanics, but at the same time they kind of started like as they were developing their planes, they were playing around with experiments, and those experiments kind of have a bricolage quality to them. They're a little bit cobbled together, but they're taking bike technologies and then trying to put aerofoils on them. And then on the right, this is one of their wind tunnel tests, which again is kind of like a little bit jankety, and kind of love that aesthetic of things being pieced together based on what you have available. This is the Wright brothers like wind tunnel that they were setting. So yeah, the first plane is almost like a bicycle mechanic having a go at doing something and learning it and experimenting through these like different tests. Bricolage, or like evidence of making like a more like repairing aesthetic as well. Like for instance, on NASA's moon lander, moon rover, there's this dust guard problem. So the dust guard came off, and they had to kind of work out a way to hitch a map and put that onto the dust guard. There's also this famous mailbox, which saved the life of 13 Apollo astronauts by cobbling together a CO2 scrubber with some plastic bags and lithium hydroxide canisters. So it's kind of like engineering, but just with the resources that you have around you in a limited way. Normally when we're designing something, you always just assume everything's limitless, but it really activates a different part of your brain when you're trying to say, okay, I've only got a limited set of pieces around, and what can you do with that? In this case, using it in a pretty extreme scenario where you haven't got, where you really don't have very many resources available. Like NASA, obviously, like on the moon, that's another instance where you're really trying to use resources in a careful way. But if you look back to Earth, I think that kind of like idea of the sustainability begins to come in. So you get the whole Earth catalog, where they're really thinking of the planet as like a resource constrained environment where you haven't got unlimited materials. It is just a blue marble. You've got to try and make the best use of what you have in like using lightweight structures. The whole Earth catalog's also got a pretty like cool self-sufficiency vibe to it. It's a lot of it's about access to tools and democratizing knowledge for construction. So you're trying to move away from that kind of like Crystal Palace, mega industrialized way of thinking towards one that's a bit more open and democratic as well. Okay. So this is where kind of like I've been working on this company. So thank you so much for having me. It's a great pleasure to be here. The whole idea of this company is taking a whole constrained set of material and trying to reassemble it into different configurations. It comes out of two areas. So it's my academic research, which is at MIT within the field of architecture. It's like this idea of reusing material, but also like a professional domain of expertise. So for the last 4 years, I've been working professionally as a facade engineer. Yeah, so previously at MIT, I worked with a lot of great colleagues on trying to find like these kind of like kintsugi style algorithms where you're trying to solve ways of getting like rubble to fit in to a target geometry, and testing out using different like solving algorithms and optimization algorithms to find a configuration that has the least overlaps and uses the rubble in the best way. Been looking at kind of like surface evaluation type algorithms, and recently trying to like do whole scale 3D scans of shapes, scan the shape and then find ways for the rubble to match up. It also bringing in a bit of like machine learning to try and help matching those pieces. And yeah, so you're trying to put together those rubbles and maybe like find ways to make it into precast blocks. Again, I'm trying to make the like kintsugi vibe, that kind of that tender respect to the material come through. But it's also just a whole bunch of rubbish waste from demolishing floor slabs and things like that. So yeah, at MIT, I was also thinking about glass. So this is from this is my thesis from 2018. The date there is wrong, but this is the 2018 thesis. So after MIT, I went out and I've been working professionally as a facade engineer. So what you do as a facade engineer, well, you kind of take a design, you take a building from someone like Snøhetta. They say, we want to build this. You don't really ask too many questions. You just go ahead and you kind of say, okay, if you want to build that, you'll need a brick masonry lintel, and we work out the engineering of that lintel. We work out the sizes, we work out ways of coordinating with the primary structure engineer. We kind of vet the design and come up with the details that allow a builder to bid on it and to allow the construction to kind of proceed. So you're there as a kind of like an expert voice for doing the really difficult exterior envelope construction drawings. So I spent like a year of my life doing this tower in Hong Kong, working on a whole bunch of different like 3D modeling of every single component because they're all curved. So we're doing a lot of verification for the contractor there. So here I'm just trying to build up your guys' sense of like, what is facade engineering? Does anybody here know what a unitized curtain wall is? Would any of you have come across like a hook-on unitized curtain wall system? It's a pretty, they're pretty niche, but it's also a really ubiquitous part of construction, right? If you think of any tower in New York or in these major cities, right? Like they're all using these kind of like hooked on curtain wall systems. So like kind of put in here and that's kind of like some of the base technology that I've been trying to reconsider in that sense. I've also been working on the Port Authority bus terminal, which is a pretty mega project in downtown Manhattan. MIT's new Department of Architecture has got crazy amounts of glass. It's like 36,000 square feet of multiple laminated, really expensive, huge format glass. So I suppose there's a part of this where you're working on these projects and it's all well and good, but at the back of your mind, you're like, wow, we're using a lot of material on all of these projects. And that's like exemplified in one of my current projects, which we're submitting a deadline for today. So sorry if my brain's a bit scattered. Got like a 50% schematic design submission for this today, but we like again, it's just crazy amounts of material and like a certain exuberance in the architecture industry at the moment, where on the one hand you kind of like end up working on these projects because that's what's happening, that's where the jobs are. But then at the same time, I'm kind of feeling like, wow, we're really not solving a climate problem that's pretty crazy right now and is looking quite problematic. So my evening job has been trying to set up this company and think about how you could have these kind of like, so let's say like code compliant and kind of like aesthetically pleasing facade systems, but also making them out of recycled material. So the mock-up that I've been working on most recently is this called the shingle facade system, at least for myself. And so you're taking irregular pieces of glass. The reason that each of them don't quite line up is you're taking like just a random piece of glass, but then working out the system that allows all of those mismeasure and random pieces to come together. So you might say like, Daniel, that's cool, but why would you ever recycle glass? Because like I can recycle a wine bottle, right? Like everybody knows you can recycle glass. So why are you bothering to recycle glass? In this like really complicated shingled facade system. So if you look at the big glass manufacturers like Saint-Gobain, and you read their product literature and you say, how much post-consumer recycled cullet do you have in your glass? So that's like, for the building you're in at the moment, imagine when you take that building apart, what happens to the glass? Will that glass be made into new glass? And it basically say no, less than 1% of the ingredients of like this major glass producer are coming from the recycling stream. They do have some pre-consumer cullet, but that material is that's like an offcut in the factory. So when you have a big sheet of glass and you cut out your windows and you have the bit around the edge, that bit around the edge it stays in the factory and it might go back to the beginning of the production line. But the stuff that goes outside into the real world, it's not recycled. And other manufacturers say the same thing. Vitro saying 0% of post or pre-consumer recycled content in architectural glass. So I think this is like a pretty crazy thing. It's like architectural glass is like no one recycles it. Every time you build a building, it's entirely new virgin sand and energy that's being used to create that material. So yeah, for the crazy like 200 million tons of glass that we produce as a society, as a planet each year, that float glass is the architectural glass, float stuff that we care about, is being turned into glass bottles or going to landfill. So you take IGUs, that IGU becomes like debris, and then maybe it becomes glass bottles. And that's great. I'm a fan of glass bottles. It's good that we can make that, but it's a shame that we can't take that insulated glazing unit and turn it back into architectural glass again. So why can you not do that? Like, explain that in more detail. So the reason is that these production lines, you kind of melt the glass, and when you melt it, a lot of like random materials can get inside. And if you take a tempered piece of glass and you have that like a piece of nickel sulfide in that glass, that nickel sulfide can expand over time, and it just like the tiniest amount of that material, and it will expand and break all of the glass. So if you're like a glass manufacturer, if you like own a float plant, and you have even a little bit of nickel sulfide in your glass, like that's a huge problem, because you're going to have to, like, if somebody has a problem with their glass, if you just built a huge major building in a local city, and that piece of glass will start shattering, and you cost you millions to pay for the replacement, like that's a huge problem. So all float plants and all glass producers, they really celebrate that they have total purity. They're like, our glass is so pure, there's no inclusions, there's no problems with our glass, it's absolute, like, perfection. But the problem is that because it's perfection, they have zero recycling, because the material that comes through the recycling stream gets dirty. Okay, so manufacturing, like, you can't fix this with manufacturing. How big is the problem, and do we, like, is glass really got a high embodied carbon? So if you look at different, like, glass buildups, every building's got a slightly different glass buildup. M.Arch did a really nice study looking at the amount of carbon associated with different thicknesses of glass. And as you can imagine, like, when you have very thick Apple Store type glass, you have a much higher embodied carbon. But if you have more residential scale glass, it's not quite as carbon intensive. And then if you look at different facade types, like if you go for a double cavity all glass facade, then you're going to have a massive embodied carbon. But if you perhaps have some good metal panel or brickwork around your glass, then you have a lower embodied carbon as well. So it can change a little bit, but in the grand scheme of things, glass, let's see, glass is the red one. So in this column, if you look at the red bars, that's the glass. And then you can see it's pretty high, right? Like within the facade is contributing definitely a significant portion to the embodied carbon. So glass is a significant part of the embodied carbon that you can see on all of these facades, like 38% here, 41%, kind of just to give you a rough sense. Glass is also mined out of riverbeds. So when you mine the glass out of a riverbed, you're damaging those, like, the natural ecosystems that might be in that river. So if you can avoid mining glass, then that's a good thing, and we should try and do that. And then on a global scale, like, what percentages is the glass in the facades contributing? Like 6% of global emissions are building construction, and the facades may be 20% of that. So perhaps glass is like 1 or 2%. No, sorry, it's like 0.5% to 1% of global embodied carbon. So yeah, it's a big slice of global embodied carbon, and I think architects don't really consider glass as a problematic material when we're working with it. We love glass, right? Like, everybody wants to make beautiful windows and views, but we don't really think about the, like, environmental consequences of this material. Glass is inert, like it doesn't degrade. It does crack, so you've got to protect it from cracking. But some of the oldest glass in the world that's recorded is coming from Pompeii. And then I think the oldest installed piece of glass that I'm aware of is 1065. But if any of you know of a window that's older, then please let me know. I want to know what the oldest window that's still in position is. Okay, so how does glass get used in contemporary architecture, and can you take it apart? Could you get to the glass if you're demolishing a building? One of, like, the common ways that a building is put together would be with, like, unitized curtain wall systems. This is where you have factory made pieces that then come together in a building environment. So this is quite a common system. It's called YKK is a big manufacturer in the United States of America. And so that just gives you a sense of that. Okay, so manufacturers can't fix this big problem. Are there any examples of architects helping? One of my favorite examples of architects trying to help within recycling glass is Brodsky's pavilion for vodka ceremonies. It's made out of, I think, 85 windows that were taken from a factory that were taken apart. And he painted the back of the glass and created an incredible pavilion for vodka ceremonies, which I love as a program. There's also some amazing architects like Marcel Rainmakers, who's being uncovered by Balbureau in situ. They recently made a beautiful book on this architect. He's more of a bricoleur for sure, taking, in this case, like, fighter jets. So these are fighter jets that have then become like skylights on a building. Super weird juxtaposition, but yeah, just showing that you can, showing its sudden like innovativeness and playfulness in the material. I really love this project by Power Bureau in situ. So what they're doing is they're taking windows out of like an existing out of demolition projects, so buildings that have been taken apart, and then creating like a kind of gallery style punched edifice, which is got a lot of insulation fit around, and then they lay timber around that to hold the glass in position. But this allows you to get really sustainable, really low carbon facades. In this case, they kind of like aligned all of the windows on the top, which I think is a really beautiful move. So you kind of celebrate the irregularity, but you have like a clear datum on the project as well. Okay, what's special about the shingle facade compared to those other examples? Well, we're kind of using the mismeasure units, so more of just like the glass unit itself, which is the fundamental building block. So I'm sure if you go to like any glass fabricator nearby your guys' university campus, you'll find that they have screw ups. So when you like try to build anything, you normally like make a couple of mistakes along the way, right? So basically what's going on here is people have ordered a window, they ordered a glass unit, and they said, I want it to be X by X, and then it turned out that that was too big or too small, or it had the wrong lowy coating, or it was too thick perhaps, like for the window frame. So there's a whole bunch of like screw ups, and this one small fabricator in Brighton, near my hometown in Sussex, he just said, okay, take anything you want. It's all available. It's all just mistakes that they've been keeping for the last couple of years. When you ask glass fabricators, like, how many mistakes do you make? The answer I've got mostly is that it's like 5%, but I think they might be underestimating to make themselves look a bit better. But perhaps 5 in 10, 5 in every 100 pieces of glass might have just been made a little bit incorrectly, perhaps. So I'm taking those kind of like mismeasured units, and they're all pretty irregular. So one of the cool things about the shingle facade system, or what I'm trying to accomplish here, is like you're taking a whole bunch of irregular pieces of glass and putting them together into a complete facade system. And by shingling, what you do is you kind of give yourself freedom in your matching. So if you try to match it as like a grid, that gets pretty tricky. But when you shingle it, you only have to match the pieces of glass in like one axis, if you will. So yeah, you're taking your library, and then you've got like a design, and perhaps this is slightly like different path through the design process, because what you're doing is you're maybe tweaking or updating your design geometry, so your target shape, in response to the library of material you have. So you're trying to like adjust and calibrate exactly the design that you're coming up with based on the material that you might have available. Yeah, so this is then looking at the tolerance, and in order to be able to construct it, you kind of want to be able to get to a high tolerance. So you don't want overlapping pieces, you want them to kind of like match up kind of perfectly. So this just gives you a sense of what it is to take a library of 100 pieces and then have different target shapes that you're trying to hit, and the error that might be associated with that. Okay. So what about the thermal performance? I'm not sure quite how regulations work in Israel. I know that you guys have pretty strict building codes over there as well. In New York, there's crazy high like requirements, and every single piece of your building has to have a thermal performance value associated with it. So like shingling is can have a cold aesthetic, right? Like the Peter Zumthor's building, the Kunsthal, that has a lot of the shingling there is open jointed, and a lot of cool air is moving backwards and forwards around it. So there are some examples of like high performing thermal envelopes that have a shingling function. There's some really bad examples. I think this building is awful from a thermal perspective, because they kind of like allow the shingles to overlap in 2 directions. That means that a lot of cool energy is going to come in through the back of the glass. So glass is very conductive. You can see these streaks are kind of where the heat is flowing through the glass. So what you've got to do is like create thermal separation and breaks, which in this case are these kind of like green pieces here. So you've got to try and control those like separations. But what is cool is once you start shingling them, you can create like a 4-cavity, like a quad cavity wall, which has got really high thermal performance. Okay, so the prototypes that I've been going through, I first started off by making some aluminium prototypes. So everything was fabricated out of extruded aluminium, but the embodied carbon is not so good, right? So although you have 0 embodied carbon from glass, let's see if I can use the laser pointer. Yes, although you have 0 embodied carbon from glass, you have quite a lot from the aluminium. It's like 173 from aluminium. And this is a bit of a sense of the processing of that glass. A few some shots of the aluminium coming together. This is very like backyard experimenting. It's the aesthetic of the Wright brothers vibe. It's not professional, but it's kind of got some professional wisdom behind it. If you guys have ever used a silicon gun before, those things are pretty interesting. Like this is structural silicon, so once you've got the glass in position, you kind of inject that silicon and it glues the glass to the aluminium. So those things are just held by this like really strong glue. The sense of how that frame was coming together. So then I did testing on this. So you kind of like do this test where you suck air. So you have a big vacuum and you're pulling air out of this plastic bag, and then you spray your facade with like loads of water, like 15 liters per minute on each square meter. And what you're trying to do is stop the water from going inside your plastic bag. You've got to try and avoid that because that's a leak. But yeah, if you can essentially suck air out and spray it with water and still have an airtight facade, then that's the key test you're basically doing when you're designing these systems. So like most buildings you guys work on, I work on in the US, and I'm sure most of you will work on in Israel as well. If you're doing something custom, it's like super important to test it and make sure that it's like able to withstand and perform in the way that you want it to. Just kind of showing some of the airflow and water movements. Oh, sorry. Yeah. This is the assembly, and each of these arrows shows where silicon's going. So you're kind of putting a silicon seal on all of these areas to accomplish that weather barrier. And silicon is a crucial line of defense. That's what's stopping the water from coming in. So there's a lot of time just spent installing silicon. And yeah, definitely gives me a lot of respect for people who are able to do this in the real world. It takes a lot of skill. It takes a lot of skill to be able to install this stuff without having a lot of little bubble holes. So yeah, it's definitely a lot of work, but this is kind of something that I'd love to avoid, using more gaskets and things like that. Okay. Oh, sorry for the noise. Another thing that gets a little bit tricky, and this is pure facade engineering right now. This is just giving you guys some intel on what is it to do a full technical engineering of something. Okay. Yeah, in this case, we're looking at wind load deflections. So facades, you may or may not know, but they typically get attached at like the top or the bottom right, and the thing that drives the sizing of that is wind. So the main thing you care about if you're a facade engineer is how much wind your system has to take. So what you're seeing here is like a whole bunch of like kind of wind loads being applied to the mullions, to those timber elements. And so we're kind of pushing a force on that element, and seeing how it deflects and transforms. And one of the tricky things in shingles is that you can kind of end up in conditions where you pinch the glass above and below potentially. So if you're pushing it like this, and then the kind of like extrusion underneath your lateral connection wants to push towards the glass unit below. So you can end up with conditions where you like end up pinching the glass. So you have to do like a whole bunch of tests to check the deflections of those units under the different wind loads. I can see the second prototype is made out of timber rather than aluminium. I've been exploring, I don't know if it's yeah, that's my okay. Exploring ways of kind of like prefabricating pieces in a factory that could then be delivered and hooked on. So there's quite a lot of cool timber systems out there, like Ryco have a great timber system where aluminium extrusions are kind of screwed onto timber elements. So you're reducing your embodied carbon by putting more timber and less of the metal. And yeah, in my system, I'm kind of like doing something roughly similar. It all comes down to this piece of aluminium which is screwed on. So you screw aluminium onto the timber, and then you put your structural silicon glue in between that cap, because you can only do the silicon glue from metal to glass. You can't glue from metal to wood. So yeah, this is some of the, you use a tape to separate it. Then you drop the glass on into that space and you inject the silicon into that space. So they've got the tape and then the silicon. So each piece has its own unique frame, which takes quite a while to build. Definitely need to find ways to be more efficient making those frames. We have custom CNCing a whole bunch of different pieces in the shed to which of these hooks. So the hooks are kind of that piece that allow it to be attached on. So this is just when it was being assembled, we had a scaffold up to support it. So it's just going to set a sense of like what those pieces are as you put them on and off. Some of the fabrication for the curved pieces. And yeah, so for the embodied carbon, I managed to get that down another 100 units of this measurement I was using, which is in kilograms per CO2 equivalent. I'm not sure if you guys have necessarily ever done embodied carbon calculations before. The way you break it down is normally under Euro codes is raw material A1 and then an A2 scope, which is transport. So the values can be pretty influenced by by the estimate that you put, like how far you're transporting some of the materials. So take it with a little bit of a grain of salt, perhaps this column, but yeah, embodied carbon calculations are really tricky because you have to make a lot of assumptions about how far material is moving, which can be difficult. And yeah, but in any case, this gives you a sense of kind of what the final result of that was. So next steps are to, yeah, there's a few explorations I'm making to explore doing some small scale pavilions or and some further testing on this like system as well to try and move towards like some built work of this in the future. I think also the other part of this is to try and encourage more of a debate and discussion amongst architects to try and get them to consider reusing material a little bit more. I think it's a polemic thing as well, trying to convince architects that we should start talking about glass, which I don't think is really on the table. Don't think a lot of architects know that it's difficult to recycle glass. So definitely out here trying to raise a discussion about that material as well. So yeah, cool. If anybody ever wants to talk more about some of the algorithms as well, please feel free to send me an email, and I have a bunch of different matching algorithms for different things, and I'm always happy to share those on if you'd like to talk, if you'd like to play around with that kind of thing as well. Right, great. Yeah, maybe I'll take a pause there. I can share my screen and come back to anything if you need, Ellie, as well. But I'll just take a pause from talking.
Good afternoon. That works. Can you hear us? Can you hear us well?
Yeah, I can hear you. Yeah.
Thank you. That was really fascinating and inspiring. I have a question from one of our faculty. He's on Zoom and he can't tune in to ask. Well, first of all, it's from Mayor. You guys know Mayor? He's saying that first of all, I was extremely impressed with like the ability to move between a very kind of practical and technical approach to the issue, but also a kind of holistic and theoretical approach. And he wanted to ask, because he's also teaching our students courses about details. How would you kind of employ this in teaching or in a curriculum? Would you say that people should kind of should the curriculum fit this kind of approach, or is it something that you gain more in your professional practice? So I guess it's a kind of question about pedagogy.
So I think Enrique Walker had one of the best studio setups for that question. You're familiar? You're all familiar with Enrique Walker, right?
Yeah. He gave a workshop here last year.
Nice. And Nofi, you were with Enrique in that studio as well, right?
Yes, and he was here last year giving a workshop for some of the students.
I think the format that Enrique has is really gorgeous for the recycling side of things, which is that you take a building and then you kind of have to double it. So you have to kind of add to or work with an existing building. But that gives you like for instance, we were looking at some Richard Rogers buildings in Princeton from the 1970s. And they all have like a certain facade system, which basically everyone was like changing or modifying in some way, shape, or form, or they were at least proposing new systems in relation to that. I think if you start with another building that has like an interesting system in some way, shape, or form, and you have to kind of respond to that system, that can give you a good starting point for then diving into details, diving into like how something is made and a certain like technical apparatus or system. It gives you history because it gives you like a sense of things being built a different way in the past, and maybe allows you to think about how they're being built in the present and how that may contrast and compare. Like I think one of the things I'm not really hitting on in the presentation I gave today is like all of the different facade systems that may have been used for like the last 50 years. There's a lot of different like styles of like holding all that stuff, and when you take them all apart, they'll all be totally incompatible with the next one. But I think if you study in another building, you work in relation to that building, it forces you to kind of think about like how a certain moment in history and how things were being made and how you may like propose something slightly different at your specific moment. So yeah, I think starting with a precedent and then trying to work against or with that precedent would be an interesting way of potentially thinking about the like material reuse question. If that maybe that's like one way. I'm sure there are lots of different ways, but that's one that comes to my head when you ask the question, Ali.
Any questions from the students? Anyone? I have another question, my question. It's a question, I guess, about scale. Kind of, we are used to think about buildings as a kind of whole from the get-go, right? We kind of start with the site or something like that. And it seems that in your case, because of how the system works, it might have a very big influence on the final design. So do you think there's a shift here in a way from detail to building, or is it something that you imagine, it would just be able to put on any kind of building, like actual shingles?
I think that's a great question. But so one of the frustrations I had with my thesis is I think I'm sure as you guys start to think about thesis within your school, or like just as you try and frame any studio project, there's always this question, like a lot of studios have a very precise site and you make a building at that site. Which is fantastic, and I love that approach, and that's how I was taught at Cambridge and a lot at MIT as well. But I think there is like another layer of, and maybe that's my job as well at the moment as a facade engineer. But there's another layer of architectural thinking which is quite systematized, right? Like there's kit of parts architects like Richard Rogers and Foster's in the UK in like the 80s. But there's also like a whole bunch of products out there, and architects don't really get involved in the products. We like kind of defer that to a whole bunch of other experts. We're not really there designing a product which could be used in a lot of different places. So I think there's something interesting about the ability to take on a larger problem through like a more of a product design, or at least architectural product design way of thinking. Like I don't know if that's, maybe there is like an opportunity for architects to get more involved into that area. You lose that kind of like uniqueness, right? Like every building is a unique thing and it has a certain role and a meaning in that place. And that's, I'm not trying to eliminate that. I think that's really crucial and important. I think if you want to try and address these large climatic problems, maybe products are an interesting way to think about
Okay. Anyone?
I have a question. Is your first of all, it was amazing, Daniel, and how you actually build the prototype and tested it. Like a lot of times, I think we build a prototype but don't really test it for its performance in the real world. So that was really impressive. I was wondering about your code and about the kind of computation of your project. And I think I'm interested in hearing more about the process of the computation, and also is the computation of this project actually can work with any scraps of any material?
Right. So that's a great question, Mark. Thank you. For the computation, it's pretty simple. But because I think I kind of like simplified the process because it's just these dumb rectangles. Like glass is kind of an interesting piece to work with in that way because it is just like two numbers, just a width and a height. And so the process that I'm using is all in Grasshopper, and it's basically you just look at all of the possible combinations of that you could be sub-selecting from. So you have a list of 100 pieces, and then you're kind of looking at different additions of the numbers. So you say we're going to have 6 pieces at the top, 10 pieces at the bottom, 15 at the very bottom, and then you're looking at different allocations. And the one thing you've got to be careful of is not repeating the same piece of glass twice. So you've got to find an allocation which doesn't, and that's where the computation gets a little bit more heavy, because you're trying to avoid like one level of your addition like adding up with using the same piece twice. You kind of have to like eliminate the you have to kind of like batch the glass into different groups based on like the size of that grouping, and then based on like the size of that band. So if you want the band at the bottom to be 2 feet, you want this next band to be 3 feet, the next band to be 4 feet, you can kind of group the glass separately for each of those bands. That helps you to like eliminate the duplicate problem. I think one other area that I like personally really enjoy is when you match up your computation to the tolerance. So it's that kind of like helps me feel a little bit more grounded in the computation as well. So let me find the right slide for that. 1 second, just sharing screen now. Okay, so the crucial thing here is like the fabrication tolerance. So when you work with glass facades, you don't really want much more than like 1/8 of an inch or maybe like 1/8 or 1/4 of an inch tolerance. So you kind of have to know how your whole system is going to come together before you can make the matching algorithm process in the first place. So I think that kind of like relationship of like drawing your system and then working with the algorithms like in concert with that is really nice. And I definitely would always see those two things happening together. There's this thing mentions the Hungarian algorithm, which is a really nice allocation algorithm as well. That's although I think it's a little bit, the Hungarian algorithm is a little bit more for the earlier rock matching algorithm, which is a harder problem. So that's when you're kind of like, you divide up your shape into a whole bunch of different subshapes, and then you say do an allocation of one set of data to another set of data. So yeah, this one's a much more complicated matching problem, and it has different algorithms associated with it. For the glass matching, it's really just finding like additions, just adding up numbers and then seeing what the total is and which one has. You were like essentially maybe doing a little bit of optimization through something like Octopus or Grasshopper, where you're trying to minimize that total error for each of these options. But if you only have like 100 pieces, you can kind of brute force that as well. So I think I just have been brute forcing it quite a lot as well, which is a bad thing to admit to.
Okay.
I have another question that might be relevant to the students or inspire them. Maybe you can tell more about the process of establishing your own kind of research / practice, how it worked, how, what are the difficulties?
Certainly, that's a great question. Sorry, I didn't include too much slides of my like journey at MIT, but I think like my main takeaway from that was, for me, the thesis wasn't like some separate project that you just do at the end. I tried to make it more something that was that I'd explored quite a lot in a few different places before I engaged with the thesis. So I did work with Brandon Clifford on kind of cyclopean matching huge stones. And that was like we were looking at Inca and like megalithic stereonomy methods, which is pretty fun. Did some work like in studios looking at concrete matching. And then some timber matching with Ellie. We were in Berlin, we were looking at like gardens in Berlin and thinking about like invasive tree species and building pavilions out of invasive tree species there. So I think there's always been like an interest in like the meaning of a material and like how you might be able to use found material in a recollage way. But in thesis, then that became like more concrete document that I could sort of had legs and imagery and kind of like I could be used as like as a basis for going forward. And then you submit that to competitions or submit that to like groups who might have money to give you to support your work to continue. So I was very lucky to get funding from the Wholesome Foundation. So I kind of took my thesis, I sent it to them for an annual award. I won some annual award. And then I kind of like maintained that relationship and submitted it for another larger award, and then won that larger award, which allowed me to build some of those mock-ups. So I would say that using the thesis as like a tool to try and apply to different funding organizations would be the path that I've taken. And yeah, maybe didn't explain that fully in the document, but sorry, in the PowerPoint. But yeah, it's in my case, I was lucky to receive funding from the Wholesome Foundation for Sustainable Construction. I think that they do have some programs for young people who are graduating or in their final year at the moment. So if you go to their website, they're definitely an interesting place to look to for funding opportunities at the moment as well.